Hi friends, we'll start this video with magnetization. We know that the electron revolving inside the atom gives some magnetic moment, right? So, in bulk material, all these magnetic moments of all these individual atoms get added up, and hence we have something called as magnetization, denoted by capital M, which is magnetic moment per unit volume. This is known as magnetization, and the units are ampere meter cube, ampere meter square by meter cube, that is ampere per meter. Now, you know what is magnetization? Okay. Say you have a solenoid. The magnetic field when I pass a current I through this solenoid will be mu naught Ni, where N is the number of turns per unit length. You know this, right? Now, if I insert a material into the solenoid like this, which has some non-zero magnetization. If I insert any material which has non-zero magnetization, say it can be soft iron or something like that, then what happens? The magnetic field increases because of this material. Okay, so the new magnetic field, let it be B, and say it has increased by the amount Bm. So my new magnetic field is B naught plus Bm. Now Bm is given by mu naught times magnetization. More the magnetization of the material, more will be Bm, more will be the increase in the magnetic field. And mu naught is the same permeability of vacuum. It is 4 pi into 10 power minus 7. Okay, observe this. I can write Bm as mu naught times magnetization, right? I mean constant times some unit, some magnetization. So can I write B naught also in the similar fashion? I mean constant times something. Yes, I can. I can write B naught as mu naught times H, where H is the magnetic intensity, and H, the magnetic intensity, is something like magnetization only, but not exactly equal to it. Okay, and H, M, both of these have same units because both of them, when multiplied with mu naught, give magnetic field, right? So, hope everything is clear till now. The basic idea is the net magnetic field is contributed by external factors, that is maybe the current through solenoid or something like that, that is B naught, and some of it is contributed with the specific nature of magnetic material, that is Bm. This part is given by mu naught times H, and this part is given by mu naught times magnetization. This is the basic idea. Now let me write the same formula in some other different form. For that, I'll have to find a relation between M and H. Actually, there is a relation. The ratio of magnetization and magnetic intensity is known as magnetic susceptibility. Like many other constants, this is also denoted by a Greek letter. This is chi. This is a dimensionless quantity because magnetization and magnetic intensity have same dimensions, right? So chi is just a dimensionless ratio. Now you know M is equal to this susceptibility into magnetic intensity, right? Let us substitute this one in our previous formula. B is what? B naught plus Bm, and Bm can be written as magnetization into this mu naught, right? And B naught can be written as mu naught times H. Now I can write M as chi into H, susceptibility into magnetic intensity. Of course, here I have mu naught. So when I take mu naught common, what will I get? 1 plus the susceptibility into H. This is my net magnetic field. And the same thing can be written as mu naught into mu r into H, where mu r is the relative magnetic permeability. It is nothing but 1 plus this susceptibility. Okay, so my net magnetic field is mu naught into mu r into h. I can also write this as mu h in simple way, where mu is just magnetic permeability. It's nothing but mu naught into mu r. Okay, or I can write mu as mu naught into 1 plus chi. Of course, it means the same thing. Hope everything is clear till now. What can we infer from that? Chi, which is the magnetic susceptibility, and mu r and mu. These three are interrelated. I mean, if value of one thing is given, the other two are fixed. Okay, this chi, this magnetic susceptibility, has another importance. It is used to differentiate materials into different categories basing on their magnetic properties. There are basically three types: paramagnetic, ferromagnetic, and diamagnetic materials. And based on the value of chi, you can classify them into one of these three groups. However, we'll discuss about this in detail in probably the next video. For now, let us solve a problem using the concept which we learned now. A solenoid has a core of material with relative permeability 400. Mu r is given as 400. The windings of the solenoid are insulated from core and they carry a current of 2 amperes. If the number of turns is 1000 per meter, this one is 1000, I have to calculate the various quantities H, M, B, and also magnetizing current IM. Okay. Okay. The magnetic field of solenoid in the absence of that core would be B naught, right? Which is mu naught Ni. This is just the magnetic field due to solenoid, current carrying solenoid. Now, B naught is what? B naught is given by mu naught times H, magnetic intensity, right? And here I have mu naught Ni. This mu naught gets cancelled. So, magnetic intensity is given by number of turns, that is 1000 per meter, and current is given as 2 amperes. So, magnetic intensity is 2 into 10 cube ampere per meter. Next, let's find net magnetic field B, that is B naught plus Bm, right? Now, or the other way of writing it, just we wrote it now before few minutes. It is mu r mu naught times H, where mu r is the relative magnetic permeability, that's given as 400, and you know mu naught to be 4 pi into 10 power minus 7, and H we just found it out to be 2 into 10 cube, right? So 4 4 16, 16 to 32, 32 pi is roughly 100, and so I have it's approximately equal to 1 Tesla, approximately equal to. Okay, next we have to find M, magnetization. Okay, the net field is given by mu naught times H plus mu naught times M, right? So from this formula I can write as net field minus mu naught times H will be mu naught times M, right? So my M will be B by mu naught minus H, and we just found out the value of B, net magnetic field, that is approximately 1 Tesla. This is a constant, you know it, and H also we found out in the first part of the problem. So just put the values, you will approximately get it to be 7.98 into 10 power 5 ampere per meter. Units are the same, right? Okay, the last part of the problem, I have to find the magnetizing current IM. First of all, what is magnetizing current? If the solenoid was without any magnetizing material inside it, I mean if there were only the solenoid, and if I want to get the same magnetic field B as I got in the previous case with the magnetic material inside the solenoid, if I want to get the same magnetic field in the absence of some magnetizing material inside, what current should I pass through this? I have to obviously pass some greater current, right? So the amount by which my current should be increased, that is known as Im. In other terms, I can say that magnetizing current is the additional current that needs to be passed through the windings of the solenoid in the absence of core, which would give a magnetic field value as in the presence of core. This was the net magnetic field, right? Previously it was B naught plus Bm. Now B naught plus Bm. This should be written only in terms of solenoid formula. So it should be mu naught Ni, mu naught N. Now the current will be different. Previously it was I. Now I have to pass some extra current, which is nothing but magnetizing current. Hope this formula gives a better picture for Im. The net magnetic field should be the same. It is 1 Tesla and mu naught is a constant and number of turns is given. Previously the I was 2 amperes. So put the same value and only one thing is left, Im. You can solve for it. You'll approximately find that to be 794 amperes. So this is your Im. Hope everything is clear till now. That's it for today, and in the next video I'll discuss about paramagnetism, diamagnetism and ferromagnetism, and with that we'll conclude this chapter. Keep watching.